Okay, now let's take the last step. We'll relax the rigid rotor expression and find the transition energies for that we expect to be able to observe in our experiment. Okay? It's a little bit messier, but it's not so bad, so just hang on. All right, if we relax the rigid rotor expression, then the rotational constant, B, which remember is h bar squared over twice the moment of inertia, this will not be exactly equal for the ground vibrational state and the excited vibrational state. In fact, usually we'd expect that B0 will be slightly larger than B1. That's because normally when the molecule goes into an excited state, the equilibrium distance between the nuclei gets a little bit larger. And that means that the moment of inertia of the molecule is slightly larger in the nu equals 1 state than the nu equals 0 state. And since I is larger, B should be slightly smaller. Okay? Very good. Now, let's work out an expression for the energy difference for this case. So for the R branch states, transition, then we had before HF equal to h bar omega naught plus j plus 1 times B1 minus j minus 1 j times B0. Simplifying this, we have h bar omega naught plus j squared B1 plus j B1 minus j squared B0 minus minus, so plus j B0. And then regrouping the terms, we have h bar omega naught plus B0 plus B1 times j, and then minus B0 minus B1 times j squared. For the P branch lines, we have HF works out to be h bar omega 0, and then it will be minus B0 plus B1 times j, and then minus B0 minus B1 times j squared. Okay? I'll let you work that out, but it's straightforward. And then finally, if we label the states according to M instead of J, where M is equal to 1, 2, 3, and so on for the R branch lines, and it's minus 1, minus 2, minus 3, and so on for the P branch lines, then we can get one nice expression that handles both cases. We would get the transition energy equal to h bar omega 0 plus B0 plus B1 times M minus B0 minus B1 times M squared. And that's the most useful expression that we're going to have for the transition energies. And I'd just like to put a box around this and talk about this result for just a second. Okay. First of all, remember in this expression that the rotational constant is h bar squared over twice the moment of inertia. And for a diatomic molecule, the moment of inertia is just 2 mu r squared. So this would, is mu r squared. So that B would be h bar squared over 2 times the reduced mass times the equilibrium distance between the nuclei squared. Okay? Be careful, by the way. This expression is only true for a diatomic molecule, like carbon monoxide. But it's not true for a polyatomic molecule like carbon dioxide, although you can easily figure out what the moment of inertia of carbon dioxide is as well. It just won't be given by that simple expression. And then omega naught would be equal to the square root of the molecular spring constant, that's a funny term, divided by the reduced mass of the molecule. Okay? Where for a diatomic molecule, the reduced mass is equal to the product of the masses divided by the sum of the masses. But again, be careful. This will hold for carbon monoxide, a diatomic molecule, but it won't hold for carbon dioxide, which is a polyatomic molecule. For that one, you have to figure out the reduced mass more carefully. And so you might have to think about that one a little bit. But nevertheless, these are the results. If we make a quick picture, what we expect then is that a transmission spectrum for such a molecule would have a series of absorption lines which would be centered around the vibrational energy. But then we'd see something interesting. The Ro-vibrational transitions would start out nearly equally spaced, but on the R branch side, they would get closer and closer together due to this term. On the other hand, on the P branch side, once again, the lines would start out equally spaced, but then they'd get further and further apart as we move farther and farther from the center, again, due to the correction term. So that's what we can look for in our experiment.